Hello, and thank you for coming to see my poster. My name is Paul Froese, and I'm a fifth-year undergraduate student at the University of British Columbia, majoring in combined math and physics. The research I'm presenting today is research I did this past summer at Triumph in the theory group, under the supervision of Peter Navratil. Our project was to calculate electric dipole moments, or EDMs, in light nuclei. In this short overview video, I'd like to share with you why we did these calculations, how we did them, and our results. So first, the why we did these calculations. As you're likely aware, the matter-antimatter asymmetry of the universe is one of the major unsolved problems of physics. Our current standard model has some charge parity violation built in, but it's not enough to account for this asymmetry, which motivates the search for CP violation beyond the standard model. And how does the electric dipole moment tie into this? Well, it turns out that any non-zero measurement of an electric dipole moment would imply CP violation that's stronger than what's built into the standard model, because an electric dipole moment requires both parity P violation and time reversal T violation. Then through the CPT theorem, this implies CP violation. An easy way to see how this works is to consider the neutron with a theoretical electric dipole moment and a magnetic dipole moment, which we know exists. We see that under these conditions, a parity transformation is no longer symmetric, and a time reversal transformation is also no longer symmetric. Thus, many experiments have been carried out to try and measure the neutron EDM. However, what they found is that if it exists, it's quite small. So an alternative is to consider the EDM of an entire nucleus, which is what we do in this research. The reason this is attractive is because the nuclear structure can actually enhance the EDM, making it more easy to measure. And such experiments to measure nuclear EDMs are planned, for instance, at CERN, and they can be done using storage rings. In order to account for these nuclear structure effects, we need some model of the nucleus in which to do our calculations. We use the no-core shell model, which is an ab-initio theory, meaning it's based on first principles as much as possible. In practice, chiral effective field theory is used to bridge the gap between the underlying quantum chromodynamics and the nucleons. Mathematically, we use a harmonic oscillator basis to expand everything, and then truncate the basis at some Nmax, the maximum allowed energy excitation. As you'll see, our results will then converge in Nmax. The key aspects of the method are the following. First, the parity and time reversal violation is introduced through this Hamiltonian here, which is based on the one meson exchange model. Notice it's written in terms of these G bar constants, which aren't actually known, so our final results will be calculated in terms of these coupling constants. This Hamiltonian, through perturbation theory, introduces a parity admixture into the ground state, which can then be used to calculate the dipole moment. In practice, this sum from the perturbation theory is hard to calculate because of all the states in the continuum. So instead, we use the Langström's algorithm, which is an iterative algorithm, to invert the generalized Schrödinger equation with an inhomogeneous term to get this unnatural parity ground state. To make sure our calculation was correct, we started by doing a benchmark calculation of helium-3. It's good we did this, as there's been some discrepancy between previous theoretical calculations of the helium-3 EDM. Our results confirm the most recent ones of Yamanaka and Hiyama. I've also shown here the Nmax convergence for our helium-3 calculation, and as you can see, it looks quite good. This brings me to our final results, located here in the top right. We calculated the theoretical EDMs of 9 different nuclei, each one being its own color in these plots. Each plot corresponds to one of the coupling constants in the Hamiltonian, as mentioned earlier. As you can see, we did indeed find that some nuclei have enhanced EDMs. For instance, the purple fluorine-19 and the light blue boron-10 stand out. What's also interesting to note is that different terms have different nuclei which dominate, showing us that we could use different nuclei to investigate different terms of this parity-violating Hamiltonian. So, in summary, the electric dipole moment is a promising way to test fundamental symmetries in physics. We've been able to theoretically calculate the EDMs of several different nuclei and found that some nuclei have enhanced electric dipole moments. This allows us to suggest these nuclei as promising candidates for experiments, such as the planned experiments in storage rings at CERN.